2K, 6.5K, 1.85K, and this is 1.65K. Two BJT circuits are connected like this, and this is 10 volt. Is it okay? And they're asking find out the current, this I. The current I in the circuit is. Now the question is, if the transistor in the figure has high value of beta, beta is very large, and VB is also given, VB is given 0.65 volt. The current I flowing through the 2 kilo ohms resistance will be, asking for I. Okay. So please observe this. The data given is beta is very large, and earlier we have seen this. If beta is very large, the current IB will be 0. Current IB will be 0. Current IB will be 0. Means transistor circuit will not take any input current if beta is very large. And if beta is very large, IC equal to IE. IC is almost equal to IE. In the normal case also IE is almost equal to IE. IC is equal to IE. But when beta is very large, IB will be surely 0, and this will be clearly equal. IC equal to IE. Is it okay? See friends, here at this point A, we'll talk about this point A. Here the voltage is given, that is 10 volt. So this 10 volt is connected to this circuit and this circuit also. Is it okay? Now there is a no meaning by this two branches, this one, because the IB current in this is 0. It means the circuit is looking like 3 resistors are connected in series, 1.65, 1.85 and 6.5K. They are connected in series, and here they are connected with 10 volt battery. Is it okay? Now the question is, what is the I? Is it okay? So if you are able to find this current, suppose this is the I, same current will flow over here also, and same current will flow over here also. So it's very easy to find out this I. How? You need voltage drop over here first. 3 resistances are connected in series combination. You need the voltage across this. Let's take the point B. Let's take the voltage VB. What will be the value of VB? VB is the source voltage, that is 10, into multiply with the given resistance, that is 1.65 of K, divided by the sum of resistances in the circuit. Sum of resistances 6.5 K plus 1.85 K plus 1.65 K. Is it okay? So when you will find out this VB, you will get 1.65 volt exactly. Is it okay? This will be the voltage over here. Now your circuit is like, here is the voltage 1.65. Now you can apply this input circuit. This is the input loop or mesh. In this mesh you can apply the KVL, so you'll get the IE. How? I'll start at this point. VB voltage is given 1.65. Here I'm getting voltage drop, and voltage drop is given 0.65. So minus 0.65. Let's come to this branch. This branch I'm getting again voltage drop, and that voltage drop is I multiply with 1K. 1K equal to 0. Is it clear to you? C plus minus and 1K. The situation is like this. So 1.65 minus 0.65, it will be exactly 1, and IE, this IE into 1K. So IE is 1 milliampere. So if IE is 1 milliampere, this current will be the 1 milliampere, and if this current is 1 milliampere, this current also will be 1 milliampere. So your answer will be 1 milliampere. Okay friends. So it's a very easy kind of thing. You can easily get it. Okay. So do practice. You will be having good knowledge about this then. Now let's take another problem, right? Let me draw the circuit. So this is the question of GATE 2014. 1 mark question, okay? And 1 minute question also. See, the question is given. Here the connected RC. RC is connected to ground. And this is the BJT and this is the PNP BJT given over here. The battery over here is VEE and 10 volt given. This is ground. And in the base, I have base resistor RB. This is given over here. This is the PNP transistor. Over here, I have V0. Is it okay? Now the question says, in the circuit shown, the PNP transistor has VBE. For this transistor, VBE is given and that is 0.7 volt. Means B to E, it's 0.7 volt. Is it okay? Now, beta is also given for the same circuit and beta is 50. Assume that the RB is 100K. This is 100K given. For V0 equal to 5 volt. If V0 is 5 volt, this they are saying with if condition, if V0 is 5 volt, the value of resistance RC, then RC is in kilo ohm. The question is like this. See, again I'm repeating the question. This circuit is given. This is the PNP transistor given over here. The base emitter drop 0.7 given, RB 100K, everything is given. They're asking RC. But the condition is, when V0 is 5 volt, what will be the value of RC? Okay, so how to proceed it? See, this is in input mesh. In this input mesh, I can apply, this is the IB over here. If the current is coming like this, ISP and IC will be outgoing. Is it okay to you? Because this is the I. So, can I apply KVL over here in the input mesh? I'll get IB. Once I'll get IB, I need IC actually. Why I need IC actually? Because, see, the question is, I need RC. And RC will be nothing but this V0 minus ground divided by this current IC. Now I have V0, yes, exactly 5, but I don't have IC. If I have IC in my hand, I can easily get RC or not. So to find out that IC, if I'll find out IB in the circuit, I'll multiply IB by beta. So I'll get IC. Is it okay? Once I'll get IC, I'll put the value of IC over here and we'll get the RC. They're asking in the question. This is 1 mark question, okay? So I'll apply KVL over here. I'll start with VEB, okay? And the VBE is given 0.7, okay? So let's start with this. The mode of point VB is given. This is the magnitude given over here, 0.7. Here in this case, this is the positive, this will be negative, okay? From emitter to base. Now, we'll start with 10, okay? Minus 0.7, okay? 10 minus 0.7, and here I'm getting RB into IB. Is it okay? Equal to 0. So let's take it to this side, and this will be 9.3 divided by 100K if I'm taking IB alone. So IB will be equal to 0.93 into, let's take it like 9.3 into 10 to the power minus 5 if I am right. And if you want to make it in micro, so it will be, you have to multiply by 10 to the power minus 1 and by 10 to the power 1. So it will be 93 microampere. The current IB is 93 microampere. Now you need to calculate IC. IC is beta IB. Is it okay? What is your beta given over here in the question? That is 50. So 50 into 93 microampere. This is your IC. Now you have to calculate RC. Now RC is, let me erase this. Five divided by 50 into 93, and this micro will become 10 to the power 6 over here. Here 5, 10 and 10 to the power 5 divided by 93. But they're asking in kilo ohm. So it will be 100 divided by 93 kilo ohm. Is it okay? So it will be nearly 1.6 kilo ohm. Is it okay? To be specific, it will be 1.07 kilo ohm. Okay. Now I'll take another problem. So this is the question, GATE 2012 and 2 marks question. Very interesting question. If you want, you can make it very long. If you want, you can make it very short and simple. Let me draw the circuit first. The capacitor C connected with 10K, and here the input is applied. See this is the AC kind of thing. Means in the circuit I have to do AC analysis as well as DC analysis. Okay, this is grounded, and over here this is 12K connected with 13.7 volt. Over here I'm taking output, so coupling capacitors are also given over here. So this circuit is fully AC circuit, means we have to use this circuit for amplification. Okay, now the question is, this is the entire circuit given. Now the question is the voltage gain AV of the circuit shown in figure is. AV means they are asking for V0 and V in. So these both are AC, right? If both are AC, means you have to do, first you will do DC analysis, then you will do AC analysis. By DC analysis you will get out RE, then you will make the equivalent circuit of this, like beta RE. Like this, you will consider collector current and you will apply all this. In this way you have to proceed. This is the standard way to proceed this type of questions. Okay, but in this question, if you observe the options carefully, they are giving like AV, mode of AV is 200. Option B is given AV is 100. Option C is given AV is 20, and the last option is given AV is 10. Okay, and they are this is not equal to, they are putting it like approximate, right? Approximately 100, approximately 200, nearly equal to 200. It's nearly kind of thing. Okay, so if the condition is given like this by option, I'll not go to this side. Simple, I'll use the circuit theory. How I'll use the circuit theory? If they're asking in approximation, I'll give the answer in approximation. Okay, so wait a minute. So if you want that your V0 and V in will be in circuit, which analysis you will do? You will do definitely AC analysis. Is it okay? Because in the DC analysis, the V in and V node are useless, because in the DC analysis all AC circuits or AC inputs will be turned off. Okay, so I have to definitely do the AC analysis. If you will do the AC analysis, capacitor will short circuited. Okay, fine. DC will be 0. And this capacitor will be short circuited. So here the voltage is V0. Is it okay? Now the question is, they're asking me in approximation. So this is base, this is emitter, and between emitter and base, what is the voltage? 0.7. 0.7. Is it okay? So 0.7 is nearly 0, I'm assuming. This is not a big value, okay? Very small value, 0.7. Let's take it 0. Now this is directly connected to the ground. So over here I have 0 volt. This is approximate, not 0 volt. Exact value will be 0.7. Let's take it 0 volt. Now you have to apply KCL over here, node analysis over this node A. Wait a minute, let me clear it. Wait. So now you have point A. At point A you have 0 volt. This is approximation because exact voltage over here is 0.7 volt. Now I'm going to apply KCL or node analysis at point A. Is it okay? So apply over here 0 connected with 2 branch only. Here the current is 0. IB is in micro ohm. Again my approximation. Sorry, the base current is micro ampere. So again this will be 0. I'm considering 0. So over here 0 minus V in. 0 minus V in divided by 10K. Okay, fine. And another branch is this. Here the voltage is V0. So 0 minus V0. 0 minus V0 divided by 100K equal to 0. Okay. So this will be Vn by 10K equal to minus V0 by 100K. So it will be 10 times. And they're asking V0 by V in equal to minus 10. But they're asking in the option the mode. So let's take the mode of it. So V0 by V in will be nearly equal to 10. Okay. So this is the way you can do this circuit in only 1 minute. Hardly 1 minute, 2 mark question. But some students will do it by long method. They will apply the DC analysis as well as AC analysis. And that is the standard way to do this circuit, because this circuit contains AC sources. And they're asking AC gain only. That AV is nothing but the AC gain. AV for this circuit will be always V0 by V in. And V0 and V in both are the AC terms. So definitely we have to do like this. But if you'll observe the question, they are giving the values in approximation. So we can, we can get approximate circuit of this given circuit. Okay. And what I have did over here. I hope it's clear to you. Let's come to the another problem. So given question is GATE 2014 question and 2 marks question. And the circuit of the question is given. Let me draw it. I'll take 45 seconds. 12 volt. R1 is 33K. This is 11K connected with coupling capacitor, and this is V in over here. Is it okay? So if you will observe in this circuit, we are mainly using potential divider biasing, right? Potential dividing biasing has its own advantages. It stabilizes the IC or beta, control the beta. This is 10 ohm given over here. But I think this particular question we have done in the last session, right? Okay, I'm sorry. So let me take another one. So this is the latest GATE 2017 problem I'm taking, okay? And 2 marks problem, and the problem is like 44K, 4K connected with 2K emitter resistor, grounded, perfectly fine. This is the base connected over here, and the potential divider circuit is given at the input stage, and obviously the VCC is given over here 18 volt. Now the question is, let me repeat the question. Consider the circuit shown in the figure. Assume base to emitter voltage VBE is 0.8 given over here. VBE is 0.8. Is it okay? This is NPN transistor, 0.8 given over here. Okay. And common base current gain means alpha is also given. Alpha is unity. Okay, now the question is the value of collector to emitter voltage VCE. They are asking for this VCE, collector to emitter voltage in volts. In volts they are asking. This is your question. Okay. Now, as we do in the potential divider circuit, we resolve the input stage. Here also we'll do the same. Let me change the pen for that. Here also we'll do the same. We'll just divide it. Thevenin equivalent will take at this point. So it will be, now your new circuit will be, this will be 18 volt directly connected with collector of the transistor only. Here is the transistor, 2K is as it is, like this. Everything is same. Now the input stage will be RTH and VTH. Okay. How to find out this VTH? VTH is the voltage across 16K. the voltage is going to divide, right? So 16K into 18 and divide by 16 plus 44, it will be 60. Okay, so 30, and this is 9, this is 10, and this is 3. So finally you are having 8, and this is 5, 24 by 5K. 24 by 5K. The value of this is 24 by 5K. So it's nearly 5K. Okay. Oh, sorry. This I collect. This is about VTH, right? This is VTH. So this is 60K. K will get cancelled. So you will be having 24 by 5. So here the voltage is 24 by 5. Okay, perfectly fine. What about RTH? RTH, across this point, both are in parallel connection. So 44K into 16K divided by summation of them means 60K. K will get cancelled, and if you will find out the resultant, it will be 11.3K. Okay, 11.3K. Now your circuit is like this. Let me raise some part. So it will be 11.3K. Perfectly fine. 11.3K. Okay, now the question is we have to calculate VCE. Is it okay? So this is the input mesh I can apply over here. So I can get current IE. Once I'll get the IE, I'll get the IC over here. And remember one thing here, alpha is given 1. What it means, alpha is the relation between IE and IC, right? Alpha IC. Alpha is 1 means IE is equal to IC. If IE equal to IC, it means beta is definitely 0. So in this case also beta is 0. In this circuit, IB is 0. Sorry, not beta, IB is 0. Okay. IB is 0. So in the input circuit, there is no current over here. IB is not given over here. I will be definitely. I'll start with the 24 by 5. So that is 4.8. There is no drop in the circuit. I'm just leaving it. Here it's given 0.8. So minus 0.8 minus 2K into IE. Is it okay to you? I applied the mesh analysis in this input circuit. I started with 24 by 5. That is 4.8 volt. There is no drop into this resistance. And there is this potential difference 0.8 minus 2K into IE. So I will go to that side, it will become plus, and this is 4 divided by 2K is IE. So IE is 2 milliampere. IE is 2 milliampere. Is it okay? Now your IE is clear. This is 2 milliampere. So alpha is 1, and definitely IC will also 2 milliampere. This is 2 milliampere. Now I have to calculate this VCE. Now it's very easy to calculate it because this is the output circuit in which you have to apply the KVL. Is it okay? Let me erase some part and then I'll do it. So at the output stage, you will start your journey from 18 volt given VCC, and you will terminate your journey and 8 ground of emitter junction. Is it okay? Because then only you will get the VCE, because VC is the voltage in between collector and emitter. So I'll start my journey over here. I'll get 18 plus minus, I'm getting drop, and the drop is 4K into 2 milli. Then I'm getting VCE. Let's take it minus VCE because plus to minus I am going. Here I'm getting 2K into 2 milli equal to 0. So finally K and milli will get cancelled. 18 minus 8 minus VCE and minus it's 4. Is it okay? So VCE is equal to 18 minus 12. So it will be 6 volt. VCE is 6 volt. You have to answer it. So your answer will be 6 volt. This is a perfectly right answer. So this is the 2 marks problem. Right? So let me take another one. Then we'll start the session. So next question is given. Let me draw the circuit. This is the gate problem. get 2000. And the problem is, this is 15 volt. RC is connected over here. Again, potential divider. 10K, 5K. Over here, it's 430 ohm. Okay, connected like this. RC is over here. This is 15 volt. Everything is okay. 10K, 5K. Yes. Now the question is, in the circuit of the figure, assume that the transistor is in the active region. Active region is given, so no need to check. The region of operation already given. Now it has a large beta. Beta is very large, so immediately it can stuck in your mind that IB is 0. IB is 0. Okay, beta is very large, I will be 0. And its base emitter voltage is 0.7. Here it's this voltage is given 0.7 volt. Okay, wait a minute. 0.7 volt. Okay. The value of IC is, now the question is the value of IC is. So the question is value of IC. Is it okay? So let me start it. This is the potential divider. I can divide this circuit and will simplify this circuit first. So your circuit will be, this will be 15 and this is RC 430 like this. This is the resultant and this is the resultant voltage. Resultant voltage will be 5 volt. 5K into 15 divided by 15 will be 5 itself. Now 10 and 5 they are connected in parallel combination. So 10 and 5 divided by 15 3 times. So this is 3.33 K. Okay. Now the question is they're asking for IC. Okay. And they have given 4 options also. Option number A is indeterminate since RC is not given. So this is IC is not given. Option A. Option B is given 1 milli. Option C is given 5 milli. This is 5 milli. Option D is given 10 milli. Is it okay? Now apply, this is the input mesh. Apply just over here the KVL. And remember IB is 0 because beta is very large. So this is 5. No voltage drop over here. And here I'm getting minus 0.7. Okay. And here minus 430 into IE equal to 0. Is it okay? So this will be 4.3 equal to 430 IE. Is it okay? So IE equal to 4.3 divided by 430. So this is 1 milliampere current. So answer is 1 milliampere. Some students will do that indeterminate because of IC is not given. RC is not given. This is RC. They're asking for current IC. So RC is not given. So they are saying that not determinate. Okay, but the exact answer is 1 milliampere. Sorry, I did mistake over here. This is 1 divided by 100. So it will be 10 milliampere. So your answer is 10 milliampere, not 1 milliampere. Okay. Now we'll start the theoretical part of this. See, AC and DC is over. Okay, fine. Now next topic will be FET, field effect transistor. Okay. The BJT is over. Now let's come to the field effect transistor. So in the field effect transistor, the field effect transistor is a semiconductor device similar to BJT also, which depends for its operation on the control of current by an electric field. There are two of field effect transistor. There are two types of field effect transistor. One is JFET, one is MOSFET. So let's come to the working of this and then we'll start it. We'll see the parameters of this. See, we have seen the BJT. BJT is 3-layer device like this. Emitter part, base part and collector part. Is it okay? This is N, P N. Okay. Now if you will connect this with this way, or you have to do it forward bias, you will do like this, you will connect to it. And suppose you want to do this reverse bias, you will connect positive terminal over here, and this is your active mode, active region. Why? Because see, here the VBE is connected in forward bias, and here this is reverse bias, so it will work in an active region. So in BJT what will happen? If this is the current IE, so it will come out. Is it okay? Because this is the NPN. IB will go in, IC will go in. Is it okay? Now see, the IC current and IB, they are combining and making IE. So this is the, the controlled current. Exact current should be IC. IC is alpha IE. Is it okay? The relation between IC and IE is given. Okay. So this IC is controlled by this IB. Okay. If this is PNP transistor also, if this is PNP transistor, so in the PNP transistor, the IE current will enter to this terminal and will come out over here. IC. As a IC, it will come out over here, and this is your IB, So who will control your current IE? We are controlling this current IE. Is it okay? The IC is not exactly IE in the BJT, because this is the controlled current. IC is the controlled current because of this base reason. The emitter current is coming over here, and due to the base holes recombination, here the recombination takes place, and because of the recombination phenomena, we are getting IB, the base current. So in the base current, we can say this is the recombination current also. So this is the working part of the BJT, and mostly related with the electronic device and the circuit. In the analog, we have to mean with the circuit. What is the circuit of BJT, and we have used it. See, in the entire BJT circuit, we have seen the biasing of BJT, in which we have seen self-bias, potential divider, ammeter feedback, ammeter resistance, collector feedback, and all, etc. So many. Okay. So we have seen some problems in which we understand how to solve the BJT problem. So there we deal with the circuit only, BJT circuit. Okay. So similarly in the FET also, little bit we know about the working of FET, and then we'll switch to the problems. Okay. Now in the BJT, see why we are calling it bijunction and bipolar device also. Why bipolar? Because in the conduction, the electrons and holes both are taking place. Okay. Both are participating in current flow in the BJT. That's why we are calling it the bipolar junction device. Is it okay? Now in the FET, what is the structure of FET? FET is also, so I can say this is the current control device. The BJT is current control device because of due to current you are controlling the current. So in actual, this is the current control, current source. At the output, you are taking current, and you are controlling that current by current control. So this is called the current control, current source. Is it okay to you? Now friends, if we'll talk about the FET. So FET is voltage control, see, voltage control current source. Okay. FET will be voltage control current source. Okay. So what is the structure of FET? FET is like, we have channel. Let's take it N channel. We have 3 terminal, drain, source, and gate. Okay, both sides, they are connected to each other inside. Okay, this is the gate terminal. So this is the circuit like this. This is the gate part. Okay. So this is the channel. Let's take it N channel. N channel means we are having only electrons over here. Only electrons you have, because this is the N channel. Is it okay? Now if you'll apply the battery over here, let's take it VDS. What will happen? The current will flow in the circuit. The current will flow. So till now this current is not, the controlled current. Our task is we have to control it. We'll control the current with the help of voltage over here. Okay. So see what is going on over here. You applied the battery output VDS. Because of this VDS you are getting current over here. Is it okay? Now this is P type. These two P type gate terminals are connected over here. And your channel is N type. Now at the first point the gate terminal is open. So you are getting some current into the circuit. Now you have to control the current. So you can control by applying some voltage over here. And you have to apply the voltage always in negative. Means you have to make it reverse bias. This junction reverse bias. This is N, this is P. P is connected with minus, so this junction will be reverse bias. So there will be depletion layer over here, and this depletion layer will become like this. Okay, and this depletion layer at some value of VGS will, very close. These two depletion layers. Let's take it D1 and D2. The two will be very close to each other when you are increasing the value of VGS. Okay. So at one moment, the current into the circuit will become constant. That voltage we call the pinch off voltage. Pinch off voltage. So pinch off voltage is the voltage where two depletion layers are very close to each other and the current become constant in the circuit. So that current we call the saturated current also. Okay. After that, if you will increase the VDS, there will be no effect in current. Is that okay? So this is brief about the working of FET. Let me come to the points I have written over here now. So FET, see this figure is given over here. This is N and this is P types of gate. See this layer is given. This is N type. This is channel. Okay. This is P type gate, and FET has three terminals. This is drain, this is gate, and this is source. Okay. Similarly in BJT also we have three things. One is emitter, base, and collector. Over here also we have drain, source, and gate. Is it okay? Now see in this figure, if you will see it carefully, the channel is given, gate is given, and we are applying the output battery over here. Because of this, the current ID will be there in the circuit. Okay, that current will be controlled by this voltage source by applying some voltage over here at the gate terminal. If you apply some voltage over here, what will happen? This depletion layer will going to increase in the circuit. If these are going to increase, it will create some obstacle in the path of current. Is it okay? So current is definitely will be controlled now. If initially you don't have any depletion width over here, the electrons are free to move from D to S. They are free. So they are creating current. Okay, but once the depletion layers are pinched off, the current will become constant in the circuit. So basically the FETs are two field effect transistors are two types. JFET, junction field effect transistor, and MOSFET, metal oxide semiconductor field effect transistor. So let's come to the FET and MOSFET one by one. Okay. So the FET has several advantages over conventional transistor. Okay. So in a conventional transistor, the operation depends upon the flow of majority and minority carriers. Bipolar junction device. Okay. That is why it is called the bipolar transistor. But in FET, the operation depends upon the flow of majority carriers only. So it is called the unipolar device. Is it okay? So if in bipolar junction device means BJT or transistor, the effect of minority and majorities are given, right? Majority. So by temperature, minority carriers are affected. Is it okay? If there is any change in temperature, who will affected in the circuit? The minority carriers affected. The majority carriers will be affected, but in very less amount. Okay. So if minority carriers are affecting the entire, the output will affect or not. So in FET, this case is absent. Means there is no minority carriers, so there will be no dependency on temperature. So who is thermal stability? Thermal stability is good for FET, not for the BJT. BJT is affecting by temperature, due to temperature, but FET is thermally stable device. So this is one of the advantages, right? The input to conventional transistor amplifier involves a forward bias PN junction with its inherently low dynamic impedance. Low dynamic impedance. See, the BJT is current control current source. Okay. This current control means the input R in is 0. Okay, let me show that, then we'll come to this part. Okay, let me show this. See, I'm telling you about current control current source, voltage control voltage source. You are having 4 types of amplifier, like voltage control current source, voltage control voltage source, and current control current source, current control voltage source. Okay, if this is the input stage, the controlling stage is the input stage and source stage is the output stage. Okay, this is input stage, this is output stage. Now at the input you may have voltage control or you may have current control. 2 things you can have at the input. At the output you can have voltage source or you can have current source. Okay, so if you have voltage control, the input resistance will be very high. The input resistance will be very high. Okay, why it should be very high? See, the circuit is like, here is the Vin, this is the source resistance, this is connected with resistance, this is Rin connected over here, and here this is your input circuit, whatever circuit is given over here. Now what is your task? The entire input should occur over here at Rin. When it is possible, when Rin will be infinity. When Rin will be infinity, the entire voltage will come over here. And this is your amplifying circuit. What you want to do, you want to give your amplifying circuit the full input. If you want to give the full input, so you need to take this Rin infinity. If Rin is infinity, entire voltage will come over here. If Rin will be 0, what will happen? 0. Voltage is 0. What will you amplify now? Nothing. Is it okay? So similarly, I'll write for this 4 terms also. Let me draw first. VC is if voltage control is there, definitely if you have voltage control, definitely Rin will be infinity. If you will have current control, so Rin will be 0. Is it okay? Now, what about the voltage source? If at the output stage you have voltage source, so I will call it R out will be 0, and if you have current source, R out will be infinite. So at the input stage, voltage control will have infinity, and output stage current will have infinity. Current at the input stage will be 0, and current at the voltage at the output stage is 0. Is it okay? So to this 4, I can, take another name also. Let me erase it first. Voltage control current source. So voltage control, your Rin is infinity. Your Rin is infinity means your input resistance is increasing. Whenever resistance is increased, we take it series. In the series circuit only, the resistance increased, right? The current source. If this is the current source, R out I'll take, because this is the output stage. Output stage is infinity. We have seen just now. If this is infinity, again at the output stage also you have series circuit. So this is series combination. The another name of this is series series combination. Is it okay? And another name of this we'll see in the third unit. In the next unit we'll see this. So another name of this will be current source, or I call it current series. Current series. Okay, we'll come into the next unit to this. What I wanted to show you is for voltage control, for voltage source and current control, what is the value of input and output resistances. I think that part is over. Now come to the over here. Okay. So now you'll get that point easily. See. So the transistor is current control current source. So what will be input resistance? Input resistance will be 0, means very low. And output resistance will be very high. Is it okay? So that's why we are saying the conventional transistor will having low dynamic impedance. The input to FET involves a reverse bias PN junction, hence the high input impedance. And if you'll talk about the FET is voltage control current source. Voltage control means Rin is infinity. And definitely in the diagram also you can see this. Wait. This is the input stage, and in the input stage you have reverse bias. Here you have N channel, here is your gate, and into gate you are applying the reverse battery. So this is the input stage and this is the reverse bias. So in the reverse bias the R is infinity. Okay. So this point is over, I think. The input to FET involves a reverse bias PN junction, hence the high input impedance of the order mega ohms. Okay. It is less noisy than a bipolar transistor. The noise is less in this. Why? Because this is the single channel, right? There are only majority carriers and no thermal effect is there. Thermal stability is good. So I can say there is zero noise or very less noise. It exhibits no offset voltage at zero drain current. If the drain current is zero, there is a no offset. Offset means, see, wait. What they are saying, it exhibits no offset voltage at zero drain current. In the BJT, if you'll see, there will be two junctions. And because of the junction, the capacitance of itself is there. So because of that capacitance, you have stored charges around it and you are getting the barrier potential 0.7 in it. But in this case, FET, there is no such conditions. So at zero drain current, no offset is there. Okay. And it has thermal stability. Just we have seen why it's thermally stable. Now let's come to the terminal from where the majority carriers, means electrons, enter the channel is called the source, designated by S. The source is just like as emitter. The terminal through which majority carriers leaves the channel is called the drain. Drain is just equivalent to collector. Okay. Carriers leave the channel is called the drain and designated by D. For N channel device, the electrons are the majority carriers. Definitely, if channel is N, majority carriers will be only electrons. Okay. Hence, the circuit behaves like a DC voltage VDS applied across a resistance RDS. If you are having only electrons in the circuit, it means it's looking like at some resistor RS, you are applying your battery. Is it okay? And because of that battery, you will get the current in the circuit. Okay. There is a no controlling effect yet. The controlling will start when you will apply some input over here. Is it okay? So, the resulting current is the drain current ID. If VDS increases, ID increases proportionally. Is it okay? If VGS is 0. What is the condition? Who will control the circuit? VGS is control the circuit. But you have chosen your VGS equal to 0. VGS is equal to 0 means in the path of this ID, you are having only N channel. N channel has its own resistance. Let's take Rn. In the path of Rn or to this Rn, you apply this VDS. this VDS you applied. Because of this VDS, you have current in the circuit, and that is ID. So this is kind of ohmic reason or not, tell me. You are increasing your VDS, your current is going to increase. So this is the ohmic reason. Okay, this is the Ohm's characteristics, like voltage and characteristics. Okay. So at some point it will be ohmic, or I can say this is the resistive activity. But at some point, that is Vp, the current will become saturated. Let's see. See this circuit. I'll show everything now in the circuit. This is the ohmic reason. Ohmic reason means you just applied only VDS. Okay. VDS you applied, you are looking at RS. RS is the circuit resistance. In the circuit resistance you have ID. Okay, ID. But at some point there is a voltage Vp. This is called the pinch-off voltage. At the pinch-off, the depletion layers will be, see, this is the gate. Let me draw it over here. This is P. This is the gate terminal. Okay. This is N channel. So they are making some depletion layer, right? Wait. Here is the depletion layer like this. Here is the depletion layer like this. If you have VGS equal to 0, VGS is equal to 0, no problem. But you are increasing this value of VDS. You are increasing. Means you are doing this negative bias more. This PN junction, you are biasing it negatively more and more. So at some time, this depletion layer will touch to each other or very close to each other. This point we call the VP, pinch-off point or pinch-off voltage. At pinch-off voltage, what will happen? The ohmic region will off now. Now this will become in saturation. At this stage, the current through this depletion layer contact will go at same pace. Means there is a constant current. The electrons will go in this fashion. So they will constitute constant current. Is it okay? Into the circuit. So now there is no increment in current. When you will increase this VDS, there will be no increment in current value. Okay, because path to flow of current is now very narrow, because two depletion layers are connected to each other or contacted to each other. Okay, so current become very constant. This current we call the saturation current. IDSS. This is the saturation current. This current is saturation current. Or I can say this is the max current. Apart from this, the current can't go. Okay, and we don't consider the breakdown region in general. Okay. After some time, when VDS will be very high, there will be, broken in this covalent bond in this depletion layer. So there will be having breakdown currents. Okay. So for the good reason or good working of the FET, we need to be within saturation or up to saturation region, because if you want to take the application of FET, you need to work FET in saturation region only. Okay. So this is the layer, or this is the characteristics, the constant current. This is the I constant. And when VGS is equal to 0, when VGS is equal to 0, the condition given. Now, see friends, if you are applying some VGS into the circuit, If you are applying some VGS to the circuit, so already you have some depletion layer like this in this way. Now you are applied the VDS. Now your VP will reduced or not. Means now at very low temperature, at minimum temperature, the depletion layer will contact to each other. Initially, if VGS is 0, and initially suppose they were taking 10 volt to come together. Now if you applied some VGS, you already provided some negative biasing or some negative layer to me. Now maybe it will be 7 volt. At 7 volt only you will get the saturation. So definitely your VP value will going to decrease now because of the application of this VGS. So in the next case, if you will apply some VGS, your characteristics will be like this. It will like this. Okay, I think the diagram is okay. Yeah, here is the diagram. This is the characteristics given at VGS equal to 0. Perfectly fine. I don't have any problem. But if you applied VGS is -1, here is your VP. So your VP is decreasing like this. This is the parabolic manner. Okay, by which its VP is decreasing. Is it okay to you? So let me come over here. Wait a minute. Wait. Now let's take it. Consider now n-channel JFET with a reverse gate source voltage. So whatever we discussed, this point is given over here also. The additional reverse bias pinch off will occur for smaller values of VDS. Definitely, if you are applying additional VGS, your pinch off value will decrease in terms of VDS. Okay, and the maximum current, drain current will be smaller. The maximum drain current will be smaller. See, family of curves are given over here. You can see your VP is going to decrease as you are applying VGS. Okay, at some point when VGS equal to exactly VP, there will be zero current, total cutoff of the circuit. Okay, we'll see. Now here, this is the transconductance curve of the JFET is a graph of the output current ID as input voltage VGS. Transconductance means you are taking output current ID and input voltage. This is transconductance. Okay. So now your ID, the output current waveform is given over here. Your ID is changing like this. At VGS equal to 0, it's this. At VGS is -1, it's like this, like this. This is the graph or characteristics of JFET, right? With respect to VGS. But now you are looking the variation in current ID with respect to VGS, the input stage. So this is the input stage. Okay. At the input stage, you are applying the VGS only, and the VGS is negative. Your VGS is negative. When current is max, see, when current is max, your VGS is 0 or not? Your VGS is 0. But as your VGS is going to increase, you are getting your currents like this. At low level, you are getting now your saturation current, or at low voltage, you are getting it. Is it okay? I hope it's very clear to you, because earlier we discussed this output characteristic, and we have seen there also VGS equal to 0, -1, -1. This is the input changing, and the output is ID is changing in this way. Okay. So by reading the value of ID and VGS for a particular value of VDS, the transconductance curve can be plotted. And the transconductance curve is a part of parabola. It has an equation. This is very important equation. The relation between VGS and IDS is parabolic equation. ID is equal to the max current, IDS as saturation current, into 1 minus VGS by, this is VGS of, means we call the VP square. Is it okay? This is the formula for ID. The drain current. Drain current is IDS as saturation current into 1 minus VGS by VP whole square. When GCS VGS equal to VP, and this condition will be off condition. So VP also I can call VGS off. Okay, so this is very important equation, current equation. So please remember it. Okay. So friends, this is all about today's class. We'll meet in the next with problems based on the FET, and then we'll bind up this session. Okay friends, take care and bye.